As we enter the last few videos in the course, we're just going to introduce one more new component, and that's going to be the field effect transistor, which is also going to be referred to as the FET. Now, if we consider what a BJT represents from the previous videos, we have to really think conceptually how it works. So we know that if we feed in or out some base current, well, what that does is it allows for a lot of current to flow between the collector and the emitter. Of course, for the BJT, we had the NPN and the PNP, but nevertheless, we could say that the BJT kind of act like a current-controlled switch. Now, there's got to be some kind of complement of this, and that's what our field effect transistor is. Now, we have a few different kinds of FETs that we looked at. We have the metal oxide semiconductor FET, often referred to as the MOSFET, and that's primarily what we're going to look at in the next few videos. In addition to that, we have the depletion mode MOSFET, and then we have the junction FET. Now, what we're going to do is ignore all of the semiconductor physics for FETs. And similar to the NPN and the PNP BJT, we have a corresponding N-channel and P-channel MOSFET. Now, it's been a while since we've looked at MOSFETs, but we know that they have 3 terminals, similar to the BJT, but a little bit different of a nomenclature. So we have a gate, denoted by the letter G, a drain, and a source. Now for the N channel, you can tell because you get the arrow going into the FET, and for the P channel, it's kind of going out of the FET. So what we can do is loosely say that if we have a voltage to the gate, well, that's going to allow current to flow between the drain and the source. So we can consider a circuit as we have here, where we simply just have an N-channel MOSFET. We have a voltage to the gate in respect to ground, which is also where the source is. And then we have another voltage V2, which is tied to the drain. And because we say that our MOSFET acts like a voltage-controlled switch, we're going to say that the gate current, so any current going in or out of the gate, that's going to be equal to 0. And from our exposure to BJTs, we can really ask, would it be so odd to assume that there's a few modes of operation? But it turns out to even make the current flow, we need to be above some threshold voltage. And this threshold voltage is what's really going to activate our voltage-controlled switch. Now, where does this voltage get applied to? Well, it turns out that it is actually going to be the differential voltage between the gate to the source. And for the N-channel MOSFET, if VGS is less than that threshold voltage, well, then we usually can assume that we are in the cutoff mode unless something odd is going on. Now, is that gate to source voltage or that threshold voltage, is that always one value? The answer is no. You are going to need to pull that from the data sheet. Now, the other modes that we have are the saturation mode, and then we have the triode mode. Now, in the saturation mode, we simply say that the gate to source voltage is greater than the threshold voltage, and then the drain to source voltage is greater than VGS minus our threshold voltage. For the triode mode, we say that VGS is greater than the threshold voltage, but now VDS is less or equal to VGS minus the threshold voltage. And the way that I always liked to think of this when I was a student was that in the saturation mode, you could say that VGS is in control, and in the triode mode, well, VDS is in control. Now, if we look at the triode mode, we can model the drain current simply like this, where oftentimes you might just see the drain current called I sub D, or it could be called I sub DS. Now, if we define the drain current, it's going to be equal to this value K times 2 times the quantity of the difference between the gate to source voltage and the threshold voltage. And that's going to be multiplied by VDS, and then you have minus VDS squared. So we know that we're going to have a bunch of voltages here, but then we have this variable K. Now, K is dependent on a few physical parameters of the MOSFET. You're going to have the width of the channel that the current is flowing, the length of that channel. You're going to have K sub P, which is equal to mu n times C subscript 0x, where mu n is the surface mobility of the electron, and then this COX value is the capacitance of the gate per unit area. So you can see that we have some intrinsic capacitance with the MOSFET. But what we can do is if we actually graph that drain current, we get something that looks like this, where we get a peak value at VGS minus the threshold voltage, but this would just be for one singular VGS. a little bit easier in the saturation mode. We simply say that the drain current is equal to K times VGS minus the threshold voltage, that whole quantity squared. So what we can do is look at some graphs. Now, if you go into a data sheet for a MOSFET, you might see something that looks like this graph here, where you're plotting VDS and IDS, or the drain current, or ID. And we can define our cutoff mode simply by kind of this flat line that we would expect if VGS is equal to 0. Now we have our triode region right here to the left of this dotted line. And if we recall what our drain current was in the triode region, we had this kind of output. And what we actually do here is we chop off this half of the curve, and we're just left with this half for each VGS. And that's what each one of these curves is going to be equal to for different VGS values in the triode region. Now we can then draw some dotted line where we hit those peaks, and then we transition into the saturation region. Now in the saturation region, we simply have this equation here. Or notice if we had some VGS value and we knew the threshold voltage from the datasheet, this drain current would be pretty constant for each VGS. Now because we're looking at a realistic datasheet value, you can see that there is a slight increase, but ideally you would get this kind of flat line that occurs. So what we can do is notice that the drain current is different for each VGS in the saturation region. So we could divide the voltage by the current, and that's going to give us some resistive value, which we call RDS. And that's going to be dynamic because we will have different values depending on what VGS we use. Now, why do we care about this RDS value? Well, recall what the equation for power is. And that's going to be equal to the current, ID squared or IDS squared, times that RDS value. And if RDS is high, well, then the power dissipated for the MOSFET is high, which means the part gets hotter. Now we know that we want to avoid burning parts up, so it's good that we have a low RDS value. And if we have a low enough RDS value, sometimes we kind of generalize this and we just use one value for it, which is given in the datasheet. Now what you might see in a datasheet is something called the RDS on value. Now it's always nice if that value is something on the order of milliohms. And in this datasheet, or this section from a datasheet, you can see that RDS, that's going to be equal to 64 milliohms, but that's conditional upon VGS being equal to 10 volts with a drain current of 15 amps. So if we look at the characteristic plot in the datasheet, what we get here is a bunch of different VGS values, and the legend for that is given right here. So at the bottom, if we look at the bottom, we would expect to start at 5 volts, and then all the way at the top, we're at 15 volts. So our bottom curve here is VGS equal to 5 volts, then up here it's 5.5, then 6, and then all of these are kind of bunched together, but that is where our VGS of 10 volts is. And we know that we're looking for the drain current equal to 15 amps. Unfortunately, it's blocked out by the box, but it's approximately right there. So if we take that down with a dotted line, we look at what VDS is, it's about 0.9 volts. So we can say RDS is equal to VDS divided by IDS. And from our crude approximations, we get that RDS is about equal to 60 milliohms. So we're pretty close. Now, of course, this would be a different value if you probed at a much different point. But nevertheless, because we are on the order of milliohms, in most cases with most circuits, it's okay to use this value. But we could say, is it precise? Is it good in all applications? And if we look at the circuit above where we didn't have any other resistors tied to it, it's debatable if it's really good value to use at all. But if you did start to throw in some resistors, say you had some 10Ks and some 1Ks, even 100K, well, sort of. And in the next few videos, we're actually going to build some circuits with MOSFETs, and it'll help us understand all of the properties just a little bit better. If you learn anything new, please like, comment, share the video, subscribe. It helps out. Thank you for watching, and we'll see you in the next video.